This is the MAT from 2013. I'm just going to do the first 10 multiple choice questions. This paper was hard. I didn't like it. So it started off quite easy and then it got really, really bad. We don't want to deal with this one here, so let's move it over and get a 0 here. Then we do b squared minus 4ac is greater than 0 for two distinct real roots, so we want to know when this is. So a is 1, b is a, and c is a minus 1. They like to give you letters that are already in here to confuse you, but don't be. A is 1, b is a, and c is this. Put that into the formula. And then we do 4 times a is minus 4a, and then plus 4 at the end. And this is indeed, because it factorizes to make this, of course, this is indeed greater than 0 all the time because it squares, except for when a is equal to 2, in which case we get 0 squared, which is 0. So we can have a to be any value except for 2, because then any other value would square to make something positive, except for 2. Good. B, so we've got sine, let's just sketch out sine. It's reflected in the line x equals pi, so that's this line here, which means this curve is going to reflect down to here, this curve is going to reflect up to here, and you actually just end up with negative sine, which is drawn here. I've put some space up here and you'll see why. The line y equals 2 is up there, and now we're going to reflect this in that line there. So now 0 is 2 away from it, so 0 reflects all the way up to here at about 4, if that's roughly where 4 is. And then this minus 1 here, that's 3 away from here, so it reflects all the way up to 5. And then this pi here at 0, that reflects 2 upwards from here because it's 2 away. That reflects to there. And then this is only 1 away from the line, so that reflects up to here. And you can see here we're just drawing a nice sine curve. This one goes back up to here because it's 2 down, so it's 2 up to 4 again. So we're drawing a nice sine curve here, and it starts at 4, so it's the sine curve plus 4, which is this one here. Good. C. So we have f dashed equals this, g dashed equals that. So we need f double dash. Let's differentiate this. If we differentiate this, we just get g dashed. That's nice and straightforward. And then let's shove in 2x, which replaces this x with a 2x. And now here, if we just replace this x with a 2x plus 1, we replace this x with a 2x plus 1 to make this. But of course, these ones cancel and we get that. And therefore, f double dashed of 2x is equal to h of 2x. There. Good. D. So they've given us 2 different graphs here, and if my eyes aren't deceiving me, these are 2 different colours, which gives you a big hint as to the fact that you're drawing 2 different curves here. Well, how can you be doing that? Well, I've seen questions like this before, so I kind of know. You add y squared to both sides, and then this is a beautiful square quadratic, which is this, and now I can square root both sides here as long as I put a plus minus somewhere. Let's just put it here. And now, of course, I'm drawing 2 graphs. I'm drawing x squared equals y plus 1, or x squared equals negative brackets y plus 1. And of course I can rearrange this one to be this, which is a quadratic the right way up with an intercept of minus 1, so that's this blue curve and this blue curve as well. And then this one, if we rearrange, is a quadratic that's upside down with a intercept of also minus 1, so that's this one here, not this one here. And so the answer is B. Nice question. E is a brutal question. Whoever wrote this was just laughing and trolling everyone. So initially when you look at this, you think, well, that's got highest power x of 4, that's highest power x of 5, differentiate it twice to get highest power x of 7. And then you look at this one, you go, okay, highest power x of 4, highest power x of 4, multiply to get highest power x of 8, differentiate to get x of 7. Good, so the answer is 7. Except when you actually do it, when you say, okay, the highest power here is actually 16x to the 4, if you were to expand that, don't care about the other terms. Here's going to be a negative x to the 5, again, don't care about the other terms. Multiply those together to get this, and then differentiate twice. So the 9 moves down to here to get 16 times 9. I can't be bothered to do 16 times 9, I just know it's 16 times 9. Differentiate again to get 16 times 9 times 8, x to the 7. So that's the actual coefficient of the x to the 7 when you do this. And here, same thing, the x to the 4 term is going to be 2 to the power 4, which is 16, x to the 4. Here it's going to be 3 squared, x to the 4, so that's 9x to the 4. Multiply those together to get 16 times 9x to the 8, and you can see where this is going. When you differentiate this once, the 8 comes down, you get this. And this term here, when you add it to this term here, the x7 is going to cancel, because it's the same coefficient. And so the highest coefficient is going to be less than 7. Thankfully, they don't ask me to check whether it is indeed 6 or whether the 6 is cancel, but it is going to be less than 7. Really, really, really rough question. I imagine a lot of people messed that up. Let's follow log rules here. So b squared equals a is what this one says. B cubed is c minus 3 is what that one says. And a squared equals c plus 5 is what that one says. And now they want me to solve this for a. It's a triple simultaneous equation, right? So what I decided to do was eliminate c. And I did that by taking away 8 from both sides here. So then I could just shove this a squared minus 8 into here. And now I've got this and this as well. So what I did was I squared this to get a squared equals b to the 4 and put it into there. And now I'm solving for b here, but I'm hoping when I solve for b I can just put it into here and get my a values, is my plan, I guess. So okay, how do I solve this? Well, I just noticed using factor theorem that b equals 2 is a solution, because 16 minus 8 is 0. So this definitely factorizes to b minus 2. Now, I could do some polynomial division, but as you'll see later on in this paper as well, I hate polynomial division. So I'm just going to spot the coefficients here. I know this needs to be a single b cubed, because b times b cubed is b to the 4. I know this needs to be a plus 4, because minus 2 times plus 4 is minus 8. And I don't know what these terms are yet, but I can find them out by just comparing coefficients. So, oh, by the way, I've also said if 2 is a solution for b, that means 2 squared and a is 4 is a solution, so I have at least one solution. I might have two. I don't have infinitely many, because this is not going to give me infinitely many b's. So the answer is either 1 or 2, or a or b, I should say. It's not contradictory either, I don't think. So, okay. Again, finding these coefficients then, well, looking over here I've got minus 1b cubeds, and over here I've got minus 2b cubeds, and plus nb cubes. So I can work out n is equal to 1, and also over here I've got 0 b's, and over here I've got minus 2 mb's from there, and also plus 4 b's from there. So m therefore is going to be equal to 2. So I can factorize it to this. Now, okay, where do I go from here? Because I want to know whether this has any more solutions. Now, the thing is, though, it's a cubic, and cubics always have at least one solution. So I thought, but I couldn't find any by factor theorem or anything. So what I thought to do was go back to here for a second and try plotting this. Now, it's a quartic, positive quartic, so it starts and ends at the top here. It's got a root at 2, I know that, so it goes through here. It's got a y-intercept of minus 8, and then we think about what this graph looks like, right? There's a few options. It must have a negative solution over here. So okay, it has another solution. It's got a negative solution over here to get from here to here, at least one. But the thing is, negative solutions actually don't matter. And this is where you need to keep your eye on the ball. Because if b has a negative solution over here, I can't do log to a negative base. So actually, any solution over here is worthless to me. I only care about solutions over here. So it does have a solution here, but it doesn't matter. Right? It doesn't matter because I couldn't use it anyway. So okay, what else could this graph do? Well, it could rotate through this side of the x-axis a few times. Right? It could go up, and hit it 3 times, because it can hit this line at most 4 times, because it's a quartic. So it could do this 3 times, but even if it does, I don't care about any of them, as I've just explained. Now, it could also hit this side of the graph a few times. It could just go through this once, and then go up and down and up again. But it can't do. And the reason that it can't do is because A apparently either only has one unique value or 2. And so for this to go back and forth again would give me 3 values for A, which isn't going to happen, isn't the case. So I think I'm confident in saying that this specifies A uniquely. While I've been explaining this, I have been thinking about, though, what happens if it goes down here, up here, and then just touches this line here in one place and then goes back up again? That will give me 2 positive B values and therefore 2 A values, which I don't think I've completely discounted in this video or in this explanation. So that's a little bit awkward, and I can't think, or I can't reason why I would know that wouldn't happen. I guess this isn't a bulletproof reason. The answer is A, and I underline that maybe hastily because it could just go through this and then touch it one more time somewhere else, I guess. So this probably isn't bulletproof enough, which is a shame, but the answer is going to be A. I'll think about that some more and see if we can come back to it. So coming at you through the power of editing, how do I justify that this quartic here doesn't come down here, have this irrelevant root here, come up through that, and then have a single repeated root here, which will give me a second value of A because I have a second positive B value? Well, you can take this quartic here, b cubed, b to the 4 minus b cubed minus 8. You don't write it in factored form, but you can just differentiate this to find the turning points. So if that's my function in terms of b, differentiate for this. The 8 just goes away, of course. Turning points happen when that's 0. Factorize out of b squared, and we'll have a turning point at 0 and a turning point at 3/4. Now, what this turning point implies here as well, because it's a b squared, is that turning point is just an inflection. It's not a maximum or minimum. It comes down through here, just turns there and keeps going down, And then at 3/4, which is of course before 2, it turns back up again and then goes through here. And then it can't turn again because it has no more turning points, and so it just goes through here and then just rides off into the sunset up here and never repeats another route. And of course GeoGebra confirms that, just slides through here, down a bit more, and then up through 2, never to turn again. So yeah, that's my justification, so the answer is indeed A. So this question is quite interesting here. We've got p of x is this polynomial. Now I can simplify that, right? There are 1, 2, 3, 4, there are n x's. And then there's 1 plus 2 plus 3 and so on to n, all just negatives. And you should know how to find the sum of consecutive integers up to n. It's n times n plus 1 over 2. So we've got nx's minus n plus 1, n into n plus 1 over 2 numbers. And here is going to be the same thing, but with n replaced with n minus 1. So that's fairly straightforward. What's the remainder when this is divided by this? Now, there's a few ways to do this, including doing some actual division. You could literally do this divided by this. I don't want to. What I'm going to do is I'm going to use remainder theorem instead. Now this is remainder theorem given one way. You can give it either way, but if x of a divides f of x with remainder b, then f of a is b. Now you're more used to seeing factor theorem problem probably, which says if x minus a divides f of x with remainder 0, essentially meaning it's a factor, then f of a is 0. But remainder theorem is just a more general expression, right, or a general form of that, whereby you just replace 0 with whatever the remainder is. But also, like, we can make this thing here more complicated, right? We can say 2x minus 1 divides f of x with remainder b, then f of a half is b, because you use whatever x value makes this 0, in the same way that putting x as a here makes this 0, that means you use a there. Putting x as a half here makes this 0, so you use a half there. So I can say this much more generally. If this is a more complicated function, I can just call, if I call this g of x, if g of x divides f of x with remainder b, then f of whatever the roots of this function are equals b. So I'm now saying, okay, if this is much more complicated, so it's some sort of function g of x, whatever the roots are, in the same way that half is the root of this because it makes it 0, and a is the root of that because it makes it 0, whatever the roots are, I can just shove those in f and I'll get b. So I can use this with these two functions then. I can say if p minus 1 of x, n minus 1 of x divides pn of x with remainder b, and b is the thing I want to find, then pn of whatever the roots this thing has, this function has, will equal b. So I hope that's quite clear. So what I need to do is I need to find when this function is 0. So I'll set it to 0. I can divide by n minus 1 here because n is not 1. And I get this, and very clearly I get x is n over 2. So, and you can see that here, if you just replace x with n over 2, you get the same thing here and here, so it just makes it 0. So if I shove n over 2 into p of n, then I get the remainder from remainder theorem. That's what it says. So I'm using remainder theorem in a really convoluted and much more complicated way than you would usually do it, but it will still work. So let's just shove n over 2 into this p of n expression, like this. And of course this makes n squared over 2, this makes n squared plus n over 2, and then minus, and this thing cancels with this thing, you get minus n over 2, which is the answer. Yeah, it's quite a nice question, that one. So h then, so you're looking for area bounded by these two graphs. Now the obvious thing to do obviously is integration, but integrating this is an absolute mess. Hopefully you can look at this and realize what type of graph that is, and that will lead you towards finding a better answer to this. I dealt with this graph first. If you rearrange this, so move the x over and then divide by this, then rationalize, you can eventually see that this is just a line. When you group the x terms up, you just get a linear x with some gradient, and then a y-intercept of this. So this is just a line here, which was probably obvious just by this, but I decided to make it more clear and see the y-intercept and the gradient and stuff. Negative gradient, positive y-intercept, I can at least see now. Now this, again, like I said, this is, if you square both sides and then move the x over, you can see it's a circle radius 2. And this is good news to see, because if I'm doing area stuff, lines and circles are generally good. I can find the area of those sorts of things. So let's do a sketch, circle radius 2, and then this line has y-intercept 2 plus root 2, so that's significantly above this point here, which is just at root 2. And now when when y equals 0, I can find the roots of this. When y equals 0, probably easiest to put it in here. When y equals 0, x just needs to equal root 2, because then because this all just goes away, so root 2. So okay, and this is also root 2, of course, because that's the radius of the circle. So it goes through this point here, which seems kind of useful. Negative gradient, of course, so it goes through there. And now, essentially what I'm looking for is this area here. So no integration is necessary, because I can do segments of circles. That's not too bad. The next step is probably the hardest, because what you want to find is this point here. Now, if you set this graph equal to this one, you're going to get into an absolute mess. I don't really know how you're supposed to do this, other than staring at it long enough and working out that this graph goes through the point 1, 1, because 2 minus 1 rooted is 1, and this graph also goes through 1, 1, because this 1 just makes this here, and then you cancel this one with this one, and root 2 equals root 2. So they both go through 1, 1, implying that this is the point 1, 1. I have no idea how you're supposed to actually get that without just noticing it. Okay, anyway, this is root 2, this is root 2, this height is 1, so the area of this triangle is a half times root 2 times 1, and the area of this segment here, well, of course, if this is root 2, and this is root 2, and more importantly, if this is the point 1, 1, then this is just the line y equals x here. And so this angle here is 45 degrees, or pi over 2. Sorry, pi over 4. But that's good, because it means that this is just a segment, a sector that I can work out, because I have the angle. So to work out this area here, I can just do this sector, which is pi times root 2 squared times 45 over 360, and then I can take away the area of this triangle, which is a half times base times height. And this is just 2, this is an eighth, 2 times an eighth is a quarter, this is just root 2 over 2, this can divide to be 1 over root 2, and we'll get the answer that we need to there. So quite a difficult question, that one. Yeah, difficult question. This one's also quite an interesting question. When you're doing these kind of iterative things, just find out a bunch of them and see how it goes. So f of 4 is double f of 2, right? So 2, if k is 2, 2k is 4. So f of 4 just must equal 1. F of 5, now 5 is odd, so it seems to be this one. If you use k as 2, you get 5 here. So f of 5 is the same as f of 2, so f of 5 is also 1. Now f of 6 is double 3. 6 is double 3, so f of 6 is just the same as this one. And so is f of 7, because you use k as 3 to get 7 here, so f of 7 is also minus 1. F of 8 is double 4, so that's going to be 1. F of 9, you use 4 here to get a 9 there, so that's also 1. F of 10 is double this, that's also 1. F of 11 is when you use k as 5 here to get 11 there, so that's also 1. And then f of 12 is double 6 here, 12 is double 6, that's minus 1. And then you continue in this vein, like 13 is going to use the 6, 14 is going to use the 7, 15 is also going to use the 7, and then 16 is going to use the 8 to become a 1. And we're going to get this series of minus 1s and series of plus 1s. And actually, notice how the minus 1, there's only one minus 1 here, then there's 2 of them, then there's 4 of them. Like, what's happening here? Well, every time you go through a number like this, it produces 2 further down the line. So f of 3 produces 2 minus 1s later, because it produces the one you get from doubling it, and the one you get from doubling it and adding 1. So every negative here will double out and produce, and so the 6, for example, produces this negative and this negative, and then the 7 produces this one and this one. So a string of 1 minus 1s gives you 2 later on down the line, and a string of 2 of them gives you 4 later on down the line. And that process will just continue, and it will be the same with the 1s, right? So a string of 2 1s here gave me a string of 4 here, and then the string of 4, after I've done with all these minus 1s, is going to give me a string of 8 later on. And likewise, this string of 4 minus 1s will give me a string of 8 minus 1s later, and then this string here, which is both of these things, of 8 minus 1s, is going to give me a string of 16 minus positive 1s here. And then, of course, this string will give me another 16. And notice, actually, as well, where these go from being minus 1 to 1, it's actually at 2n minus 1, right? From 7 to 15 to 31, and then 63, which is kind of interesting and worth thinking about. But eventually you end up with all of this, right? And this is the sequence. And now we just need to add all of these together, which is easier said than done, except for a lot of these things will cancel, right? So, okay, we can do the easy. So these 4 minus 1s cancel with these 4 positive ones, these 4 and these 4. And then these 2 cancel with these 2. So here we've got 1, 2, and then minus 1 is 1 in total. So up to here we just have 1 in total. Everything cancels except for this extra one here. And then here, these 8 ones cancel with those 8 minus ones. These 16 ones cancel with those 16 minus ones. We've got 32 ones here, and only 5 minus ones. And so 1 plus 32 is 33, minus 5 is 28, and we have our answer. I thought that was quite an interesting question, and requires quite a lot of problem solving and thinking on the fly, because you've probably never seen anything like that before. So yeah, I approve of these questions. I don't approve of these questions, which are absolutely brutal to do for how many of marks it is. Is it 4 marks for one of these questions? Absolutely ridiculous to do this in 4 marks. Anyway, we need to try and sketch this. So okay, we sketch it from 0 to n. I'm obviously just going to sketch it for a little bit. Now, when x is 0, 2 to the power 0 is 1. The floor function of 1 is just 1. So this is just at 0, 1. When x is 1, 2 to the 1 is 2, floor function of 2 is 2. So that goes up to 2. Now what happens in between? Well, it doesn't just go from here to here, right? What it does is it goes flat, because 2 to the anything less than 1 is something slightly less than 2, and when you floor function that, it just becomes 1. So this is just a flat line here, and then jumps the moment you hit 1. Now when you put in 2, 2 to the 2 is 4, floor function of 4 is 4, but again it doesn't just go to here, and it also doesn't do it flat either, because there's a number here 3 in the middle that eventually when you start getting to, you're going to jump up to there first. So okay, when you put in x is slightly bigger than 1, 2 to something slightly bigger than 1 is just above 2, floor function is still just 2, right? So you go across for 2 to a bit, but when you hit log to base 2 of 3, that's when you jump up to 3, right? When you hit that value, then you start jumping up to 3, and you continue with that until you hit 2, where you jump up to 4. Now why log to base 2 of 3? Well, of course, because that's the thing. If you set that equal to x, you literally get 2 to the x equals 3. It's the thing that you raise 2 to eventually get to 3. And of course, once you're there, the floor function just keeps you at 3 for a bit. And the same thing sort of keeps happening. So when you put in x is 3, you get to 8. But again, that doesn't happen all the way there. Log to base 2 of 5 needs to come first, and that's what holds it down at 5 here. So you're at 4 from 2 to log to base 2 of 5. Then you jump up to 5, and then you jump up when you hit log to base 2 of 6, which I don't have space to write in. And then when you hit log to base 2 of 7, you jump up again. And then finally, when you hit 3, in other words, log to base 2 of 8, you jump up to 8. And our job is to add up all of these little rectangles that we're going to get here. Not just up to 3, but all the way up to n, which sounds like a ridiculous task, and it absolutely is a ridiculous task, but we're going to try it anyway. So this area here is just 1 times 1. And then we have a little rectangle here of height 2, width log to base 2 of 3 minus 1. So those are our first 2 rectangles. Then this rectangle here is 2 minus log to base 2 of 3 times the height of 3. And then this rectangle here is 4 times log to base 2 of 5 minus 2 is the little distance there. And then the next one is 5 times log to base 2 of 6 minus log to base 2 of 5, and so on. You can see, hopefully, a pattern's going to start getting made here. The next one will be log to base 2 of 7 minus log to base 2 of 6 times by the height of 6. So these numbers are just increasing by 1 at the front here, because the rectangles just get 1 taller. And then these logs have this nice little pattern of 6, 5, 7, 6, and so on. And it's easier to see, actually, if I write these maybe, because these special cases at the start here mess the pattern up. But if you write 1 as log to base 2 of 2, and 2 as log to base 2 of 4, the pattern becomes much more clear much more quickly, that it's firstly just this, then 3, 2, 4, 3, 5, 4, 6, 5, 7, 6 in the logs, right, every single time. And the outside number just increasing by 1 every time, because the rectangles are just getting 1 taller every time. And this doesn't continue indefinitely, like I've sort of suggested here. It goes up until your last number of n at the end here, which is going to be this here. Now, let me just explain where this comes from. The last rectangle, like when we got back to, did I even write it in? If you're thinking about this picture here, if we were stopping at 3, the last rectangle is not 8 tall. It's not 2 to the power 3 tall. The last rectangle is 2 to the power 3 minus 1 tall. right? Because there's no rectangle to add here, it's just a strip. So the last rectangle, if your sum equal to n, is 2 to the n minus 1 tall. So that's the height of the last rectangle. And here, the last gap is going to be n, just like we had for 3 here, is going to be n minus log to base 2 of 2n minus 1. And again, it's not 100% clear where this comes from, but if you write n instead of that as being log to base 2 of 2n, then it becomes clear where this is from, because we can see the pattern where the logs are just 1 less than the previous one. And if I write this as that, it becomes clear that this input needs to be 1 less than this one is. Right? It's clear why this should be n, because that's the last number. So that little width of rectangle is n minus the log before it. And if I change that to that, it becomes clear that that one needs to be that, I think. Hope it is clear anyway. So okay, now what's going to happen? Well, look at this carefully. Log to base 2 of 2 minus 2 log to base 2 of 2. So that makes minus 1 log to base 2 of 2. 2 log to base 2 of 3 minus 3 log to base 2 of 3. That's going to make minus 1 log to base 2 of 3. 3 log to base 2 of 4 minus 4 log to base 2 of 4. Every single time we're just going to end up with minus 1 of each log, all the way up to the last one, but this one doesn't have anything minusing away from it because the series pattern stops there. So this one is the exception. This one is just going to appear this many times, and I've written this back as n again, just because. Now here I can factorize out a minus 1 from all of these first few terms. I can also expand out this, and then here I can use log laws to say that this is just 2 times 3 times 4 times all the way up to this, which is just 2 to the n minus 1 factorial. So it's going to make this. And now I can see I'm looking very close to one of these answers. I haven't quite got it. And this is because I just need to write n again in a really tricky way. I need to write it back as this again. I need to write n as log to base 2 of 2 to the n. And now I can see if I factorize out the minus 1 again to make it look like this. So I've just shoved this into a bracket with this guy and put a minus in front. Now I can multiply this by this as well to just make 2 to the n factorial, and now I have exactly the answer required. I thought that was an absolutely brutal question for a multiple choice exercise like this. I was very proud of myself for actually getting it. I don't think I would have done an exam. But yeah, that's the entire paper. Thank you for watching.